Hello, in this video we're in the multiple linear regression setting and we're going to talk about centering and scaling the design matrix. Now so far, except for in one video, in actually video number 2 in this playlist called General Linear Models Regression, we talked about centering of the design matrix, but usually we keep it in what I'm going to call the natural variables format. There may be other names for that, where we just y is equal to x beta plus air, where we're in this model, you know, beta 0, beta 1, x1, beta 2, x2, all the way to beta k. And the units are left in the original format. And sometimes that can pose problems. If these units, say for x1, are quite large and the units for x2 are very small, then often this x1 variable will dominate the model, sort of rendering this one not useful, even though it may be. So there's ways to combat that, and that's what we're going to discuss briefly. The centered model, as I mentioned, we talked in previous video number 2 in the list, where you just subtract the mean of that variable from each variable, and then you add that into the model. So it's a variable minus the mean, the variable minus the mean, etc., all the way down. And we actually showed in a little bit in this video number 2 that the least squares estimates for beta 1 through beta k are exactly the same. The least squares for beta 1 through beta k are the same as in model 1. So centering it, actually, and if your goal is to interpret the beta parameters, centering is not a bad thing to do. Now it turns out that the least squares estimate for beta 0 star, when you center, is actually y bar. It's the mean of your y's, which I find intriguing. And we may talk about that in later videos. Now the scaled model, sometimes called a normalized model, what you do is you take the original variables and then you divide it by its length. And then what that does, and so the overall length of this vector, remember if it's in a design matrix, is 1. And you do that for each variable. And that puts each variable in quotes on the same measuring stick. The units are very similar. And so as in the case where you have one the units are so much larger than another unit, then this puts them on the same playing field, and it may turn out the one with very small units may actually be better than the larger one. Anyway, so that'd be a reason to scale it. Also, another reason to scale is when we're dealing with multicollinearity, which deals with linear combinations of these variables. And the next 3 or 4 videos we'll get into a lot of detail on multicollinearity. Now the norm, or the length of this variable, can be thought of as this. It's the dot product. So this is the squared length. So the length is actually the square root of this. So it's the dot product of the vector, or you could think of it as the sum of the components of that vector. Now for the least squares estimates, note that I put a tick because these are a little bit different than the previous model, but there's a formula. The least squares estimates for the betas in this model are just the length of the vector times the least squares of the original beta parameter. So we can go back and get them. Now the beta 0, or the intercept term, is a little bit different, and we won't deal with that now in this video. Now centered and scaled means we subtract the mean first, and then we divide by the length of this vector, which is, it's the norm, or the square root of the dot product of this vector. Well, that turns out to be this. So SI squared is the sum of each component minus the mean squared, down that whole length of the design matrix. So I put double primes here because the least squares estimates for the beta parameters in this model is SI times beta I, the least squares estimate in the original model. So we can obtain them back. So they're one-to-one formulas for each other. Here, since we're centering, least squares estimate for beta 0 double prime is the mean of the y's again. So it's actually the same as this one. It's the mean of the y's. The interpretation of the beta parameters depend on which model is used. And there's pros and cons with all of these models. And so, but however, the fitted model, Y hat, is the same for all of these. No matter which one we use, the fitted model is the same. And so that tells us that if it's convenient to use, to scale or to center and scale, because the objective is to find multicollinearity, that it's nice to know that it doesn't affect the fit of the model. And we'll prove that later in this video. So if the fit's unaffected, that means the residuals, which is the data minus the fit, is unaffected. And anything associated with the standard deviation of the fit's unaffected. Press statistics, which we'll get to later in this video series. Anyway, so that's a kind of a neat result. And a little surprising to me. So X1, this is the natural variables model. We have a 1 down the columns, and we just have the natural parameters. It's variable 1, variable 2, variable K, and this is the design matrix for it. Now in model 2, when we center, we take the variable minus the mean, and then replace it for each of these variables. Now, why don't we do that for this first column? Well, what's the mean of 1s? Well, it's 1. 1 minus 1 is 0. So you can't center this first column, otherwise it wipes it out. So model 3, the scaled model. So you take the natural variable divided by its length, and you do that for each observation, and the same for the second, the third, and etc. Now there are cases where dividing by the length of this variable is actually smart. So when we get into variance proportions, I think it's smart to scale this first model. So when you scale it, some people don't scale this first column and some people do. And if we were to do, the length of this is the square root of n, so you just divide the square root of n by each of those. Now here, when we center and scale, it's this: subtract the mean and then divide by the length of that vector. And so actually the length of each column is 1 here. Not this one, but you could if you scaled it too. The length of this is 1, length of this is 1. The mean of this vector is 0 because we're centering it. And this is the centered and scaled model. Now, as you remember, the hat matrix. So you take the design matrix, and to find the hat matrix for that model is the design matrix, X1 transpose, X1 inverse, X1 transpose. This is the hat matrix. And we know it projects onto the column space of X1. That's the way it's developed. And so the fitted model is you take the data and pre-multiply by the hat matrix, and then it puts a hat on Y. That's actually why they call it the hat matrix. So this is the fitted model for model 1. And then we can repeat for each of models 2, 3, and 4, and then find the hat matrix, multiply it times the Y, the data, and we get a fitted model for each of those. Now, one thing that we're not going to prove, but the column space of each of these are the same. And here's a little, let's just look at this. So this is 3. So the original X1, it doesn't have the length here. But if we divide a column by a constant, it doesn't change the rank or the span of this matrix. So we're not changing the column space from X1 to X3. Now if we subtract the constant and divide by a constant, it also doesn't change the span. So going from 1 to 4 doesn't change the span. The column space spans the same vector space, subspace. So anyway, but H1 and H2 are perpendicular projection matrices. For more details, see previous video 23, previous video 25. I also have videos on perpendicular projection matrices, titled that, in my playlist in Matrix. So the theorem is that all these fitted equations are the same. All the fitted values are the same. And now stated without proof is that the column space of each of these 4 matrices is the same. And I kind of gave a brief heuristic argument of why. But the length of this video is not going to let me keep proving stuff. So by theorem P4 in perpendicular projection matrices, the perpendicular projection matrices are unique. And so since H1, H2, H3, and H4 project onto the same subspace, which implies that these perpendicular projection matrices are all equal. And so thus when we take H1 times Y, H2 times Y, these are all going to be the same. But this is how we find the fitted model. And so all the fitted equations or models are the same, and that's a quick proof of why they are. Now, we'll go into a little more detail into this centered and scaled design matrix, mainly because we're going to use it in the next 3 or 4 videos. So let's look at the centered and scaled design matrix. So in 4, we had a column of 1s, and then we had the centered and scaled columns here. So let's examine the ith column of this matrix. So these deal with our predictor variables. Now this deals with the intercept term. So the ith column in this, we're going to let it be xi star. You know, using our software notation, you know, we would be a blank comma I, so we just grab the ith column of this matrix. So if we add up the elements in this ith column, which is what this vector product does, we get this. Now xi is not indexed by j, so it comes out and we get this. So we took the sum in. Sum of xi is this, and the sum of this constant that makes n of them, and we get this. But xi bar is, you know, the sum divided by n, so the n's canceled, and we have the exact same sum, so it's 0. Now the vector product of the ith column with itself is this. So this is the ith column, and then we have to transpose the ith column. So essentially we take the first 2 times each other, the second 2, the third, all the way to the kth, and we get this. I mean the nth, and we get this. Now this is constant in regards to that, and we're left with this sum, but that's exactly what this is. So those 2 cancel, and we're left with 1. Now the dot product of the ith column and the jth column is this. You set it up similar to this, but of course, you know, we would sum it to this. Now, if we divide this top part by n minus 1, and then divide this bottom part by n minus 1, we get this situation here. We went ahead and took the square root, so we get n minus 1 squared, but it comes out as n minus 1, it cancels there. And then we get this. But this right here is the correlation, the sample covariance between 2 vectors, and then the sample variance of those vectors. And we're going to call that Rij. So it's a sample correlation. Now, maybe it's a little silly because we're dealing with constants in this setting, but if they weren't constants, this is how we derive the sample correlation coefficient for these 2 vectors. Now, so with this knowledge, if we take x star transpose x star, we actually get this sample correlation matrix, right? The columns dotted with themselves produce a 1, and any other column, you know, produces the sample correlation, and so we get this sample correlation matrix. Now, if we take x4 dotted with x4, now remember, x star is actually a component of x4. So if we look at this piece x4, it's this, and the transpose is this, and then we do the matrix multiplication on this, we get, you know, 1 times 1, but it's a vector of 1, so it's n. And then if we add up any column, we get 0, and this ends up being the same, so we get 0, and then that is this, so it's x star prime x star. We need that for this next theorem. And so I didn't know where to put this theorem in this series I'm doing, but this one ends up being a good spot. We're really going to use it later. So let's let xi be the ith diagonal of the hat matrix H. Then we're going to show that the ith diagonal of the hat matrix is between 1 over n and 1. Okay? Now, since H, well, here's something interesting. Well, we'll get to in a second. So since H is idempotent, hat matrix is symmetric and idempotent. And idempotent means H squared H. Then by theorem 8 in a video I called idempotent matrices, we proved that any diagonal element of an idempotent matrix has to be between 0 and 1. It's required. And so thus, that proves that the diagonal element, any diagonal element, is less than 1 by this theorem. Now, since the hat matrix is unique, no matter what design matrix we use, we're going to use H2 to prove this, right? And it really doesn't matter which one we pick because it's unique. It's 100% identical. And actually, go through the math on that. It's kind of fun to prove. So we're going to let H2. So let X2 be a column of ones, and then X star is the, and I'm going to flash it just so we on the same wavelength. It's the centered model, right? We only subtract the mean of the column, each column from itself. So when we do X2 star or X2 transpose X2, we get this, and then when we do this multiplication, it ends up this way. Because it is centered, when we add up each column, it's 0. So that's what this product represents. And then this one too is the column sums, which are 0. And then this is whatever it is. Now X2 inverse means, and since this is block diagonal, we just take the inverse of each of the block diagonals. Then if we multiply, we're building up the hat matrix in steps here. That's what we're doing. So now I want to pre-multiply by X2 because that's, we're building up to the X matrix. So this right here is X2. Remember, it's a vector of ones and then this column, but we're going to just take out the first column of X star, and then this is a column of 2, or the rows, first row, and this is the rows 2 through N, and I'm using R software notation for that. Because when we do this multiplication, I kind of need to separate it out here. Now, a lot of you will not need this, but the way my brain works, I do. So I take this row times this column, and we get this, right? That's 0, 0, 1 over N. That's just the number 1. Now this column times each of these columns, we end up getting this first row times this matrix here, which is this, right? Not this, I mean, we're multiplying it by this, right? So we just get that matrix back. And sorry, my hole there. So that's an inverse. It's the same as this one. And then here, this is N minus 1 rows. When we just take the first row times this, we get N minus 1, and the second row times this, we get 1 over N. I mean, every time we do this multiplication, we just get 1 over N. So this is a column of 1 over N's. Now we take this times this, so the 1 and the 0 is 0, then we get this multiplied by this, and that's what this represents. But now here's the big step. So this is just a column of 1 over N, right? And this is 1 row times this, and this is all other rows. So if actually it's an augmented matrix, so if we combine those, we get this. Now let's post multiply by X transpose, which is this. Now this times this, we get this matrix of constants, 1 over N, and then we get this matrix times that, which is this. Okay, so now how do we find the ith diagonal of this? Right, this is a matrix, this is a matrix. Well, we find the ith diagonal of this, but this is a constant matrix of 1 over N, so it's 1 over N. In the ith diagonal of this, we have to take the ith row of this, and actually the ith column of this, which ends up being the ith, yeah, so the ith row of this and the ith column of this, but it ends up being the ith row, right? And then multiplied by that. And that's what this represents. Which is, since this is positive definite, or at least definitely semi-positive definite, this is always positive. So if we get rid of this, then the ith diagonal is always bigger than 1 over n. And that's the proof. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.